So we're going to start with this one. This is summer 20. Okay, question paper 2-3. Starting with the first one. He's saying give two observations for this reaction, that it's barium, and that barium is reacting with oxygen. So two observations. So any idea what the two observations are going to be?
White precipitate.
White solid, not a precipitate. When you use the term precipitate, that basically means some solid that is forming in a solution. So it is a solid that's forming. It's going to be a white solid that's going to form. Like, it's not in a solution, so you can't call it a precipitate in this case. So, what's the second observation for this one? Okay, remember your flame tests. Okay. If I just open this, I just sent you the analytical chemistry board as well. So remember your flame test. Okay, what type of, when barium burns in oxygen, what do you get? Not analytical, inorganic. This one. Okay, what is the flame test of barium? Koi idea kisi ko? And let me go through all of them. Okay, in period 3. The period 3 tests are these ones. Okay, you should know all of them. Okay, what happens when sodium burns in oxygen? It produces a bright yellow flame. Magnesium burns in oxygen, that produces a bright white. Aluminium also a white flame. Silicon has a very slow reaction. Okay, phosphorus has a vigorous yellow flame. It's a vigorous reaction, and a gentle blue flame for sulfur. Okay, remember these flame tests. And for group 2 as well, you should know the flame test. Okay, apple green is the color of the flame when barium reacts with oxygen. Okay, scarlet red, red scarlet flame is strontium. Brick red is calcium, and white for magnesium. So remember your flame test. So in this case, this one is going to be, the other observation is going to be, it's going to be an apple green flame. So you okay. To write an equation for the reaction, we already did that. You just need to balance this. So there's going to be 2 of this and 2 of this. The next part is there's calcium carbonate, which can be converted into calcium hydroxide in a 2-step process. Describe how the 2-step process is carried out to convert calcium carbonate into calcium hydroxide. Include relevant equations. So how do you convert calcium carbonate into calcium oxide?
Decomposition.
Okay, so you need to basically heat it. So you're gonna heat it, and it will decompose even in a Bunsen burner. So heat in a Bunsen burner, I think. It's gonna check color. Heat in a Bunsen burner. What do you do next to turn
Addition of water in calcium oxide.
Okay, so you add water to it, and it turns into calcium hydroxide. That's about it. It's a 3-mark question. Let me just open the MS as well. Okay, how are the 3 marks distributed for this one? Okay, S20 and MS. Okay, so for this one, the 3 marks are heat followed by water. I mean, that's it. I mean, you had to write the equations as well, which I think we did write the equations as well. Name the type of reaction occurring when calcium carbonate is converted into calcium oxide. That is decomposition. ठीक है, वो भी आपने कहा भी था. ठीक है, that one is decomposition. State one common use of both calcium carbonate and calcium. Common use. What are they used for? You will have a question. What's
fertilizer?
No, not fertilizers. Fertilizers are NPK salts, acidic soils. ठीक है, most that's neutralize. They neutralize acidic soils. You can remember fertilizers, Joanna, they are NPK salts, which are basically ammonium or nitrates or phosphates, TK, anything, these compounds. So moving on, the next part is gallium is a silver gray solid. Aluminium and gallium share similar, when they say share similar chemical properties, so he's not talking about gallium, he's basically talking about aluminium. So all you know about aluminium, you're going to write about it in this. Construct an equation for the reaction of gallium with when heated in oxygen. So think of it as aluminium being heated in oxygen. It's going to form. They gave everything. It's gallium. They even wrote the formula, so that's kind of easy. It's gallium, and you can balance this. Always write a balanced equation. Reduce the oxidation number of gallium. I mean, you're talking about aluminum, so that is +3. Complete the table by predicting the formula of each gallium-containing product formed when gallium oxide reacts separately with hot aqueous hydrochloric acid and with hot NaOH. So now remember, aluminum oxide is amphoteric. Okay, that is amphoteric, and be careful with these inorganic notes. I mean, make sure you prepare them carefully because recently a lot of questions are coming from inorganic. So this one, aluminum oxide is amphoteric. It reacts with both HCl and with NaOH. And you're going to get AlCl3 or NaAlO2 in the other one. So the answer to this one is that gallium oxide with HCl, it's going to form gallium chloride, and with NaOH, it's going to form it was NaAlO2. Okay, I'm just going to replace the Al with gallium. So Al gets replaced by, and that's it. And for this formula, there are many different ways you can write this. I mean, there's not only one acceptable. There actually, this thing has many different versions. Shayad data, maybe MS, maybe it's going to be given that way that you can see that there are two different versions. You can either have NaAlOH4 or NaAlO2. So I'll add this over here as well. That this particular formula over here has many different versions. So you can also call this Na with Al and OH4. Or iske alawa bhi there are even more versions of this. So there are many different ways of writing this formula over here. But just remembering one of them would be sufficient. As I state what is meant by the relative isotopic mass. So it's the average mass of an isotope of an element compared to 1/12 compared to 1/12 the mass of a carbon-12 atom. A sample of copper contains two isotopes. Copper is 63 and copper is 65. The relative atomic mass of the copper in the sample is 63.5. Calculate the percentage abundance of each of these isotopes. Show your working. So you've got copper, which is 63, and you've got copper, which is 65. So there are two main isotopes of copper. Now, you don't know what the percentage is. So if I say that I have in the sample, there are X% copper. So the amount of copper 65 would be 100 minus X%. I mean, what 100 minus X%. So what that basically means is that if there is 20% copper 63, 80% would obviously be copper 65. There's 40% copper 63, 60% would be copper. So it's going to be 100 minus X. So I know the percentage in terms of X. How do you calculate the AR of a molecule? It's the percentage abundance of the element into the isotopic mass. And you sum all of them up. So basically we have the AR, which is 63.55. I know what the average is. So first one is X over 100 into 63 plus it's 100 minus X over 100 into 65. I need to solve this. So I'm going to get rid of the 100 at the bottom. So it's going to be 6355. Somebody could try and solve this. 63X plus 100 into 65, that's 6500 minus, I think, 65 minus 65X, right? So if is this correct? Did I make any mistakes? 63X minus 65X and plus 6500 looks fine. For the moment, it's 655. What is 655 minus 6500? That's going to be, what do you get? 145? You could confirm, Carl. Is this 145 if I...
Yes, 145.
And this is going to come out to be minus 2X, right? So X...
72.5.
So you divide by 2 and it comes out to be, X comes out to be 72.5%. So the percentage of copper comes out to be 72.5%. So दूसरे की क्या हो गया? That's going to be 27.5.
Yes.
I said 27.5, right? So you've gotten your answer. Remember this formula. Name the type of bonding within a sample of solid copper that's metallic. Okay. And you're being asked to draw a label diagram to show the bonding of a metallic bonding, basically. So make sure draw atoms like really closely packed. Okay, they shouldn't be really far away. And this is O levels. They're a bunch of positive ions. Metals like to lose electrons, so they're all kind of positively charged ions, and the electrons are roaming around delocalized in the middle between the gaps. So it's a metallic lattice where you have a regular arrangement of metal ions in a sea of free moving electrons. Now, the next part is you have to write the electronic configuration of copper, which is 29. So copper is one of the special cases. It should be 1s2, 2s2, 2p6, 3s2, and 3p6. And then you have 4s2 and 3d9. But remember this, you're not going to follow the Aufbau principle over here. It's a special case. No, I'm saying you're not supposed to show gaps. Like, draw them as close to each other as possible. I mean, just a slight gap, but even if you don't show any gaps, that's fine. What I was saying was that some people make a lot of gaps, so just don't make big gaps between them. I say, anyways, what is wrong with this electronic configuration? Why was copper a special case?
3d10.
Copper is actually 3d10 and 4s1. So copper doesn't really follow the Aufbau principle. The most stable electronic configuration of copper is 3d10 and 4s1. Now you've got this question. It says the student provides a sample of hydrated copper to sulfate so this is probably about finding this X. So you have to value the value of X. Student dissolves the sample of copper to sulfate in water and adds it to an excess of potassium iodide to make a total volume of 250 cm³ of solution. So I think this entire solution is 250 cm³, right? So he mixes it with potassium iodide. The amount of iodine produced during the reaction is found by titrating a sample of the solution with sodium thiosulfate. 25 cm³ of the, so out of this 250 cm³, which contains iodine, obviously, just a tiny sample is taken for titration, which is 25 cm³. So 25 cm³ of this solution requires 20 cm³ or 0.1 mole per dm³ thiosulfate. So it's this one. So this is how much? 20 cm³, and the concentration is 0.1 mole per dm³. So calculate the amount in moles of copper to sulfate present in the original sample. So we have to find this. So now when you answer this question, it's just a 2-mark question, but make sure you write everything very, very neatly. First thing, neatly write that you're trying to find the moles of S2O3 ions. How do you find that? It's concentration times volume. And if you do that, it's going to be 20 divided by 1000 into 0.1. And when you solve this, show you're working as much as you can. So how many moles do you get?
2 into 10 raised to power minus 3.
So you found 2 into 10 to the power minus 3 moles. So it's 2:1. So you're going to try and find the moles of iodine now. So moles of iodine would be 2 times 10 to the power minus 3 moles divided by 2, right? Which would be 1 into 10 to the power minus 3 moles. Now, those are the moles in the 25 cm³ sample. Then you're going to try and find the moles in the 250 cm³ sample. So the moles of iodine in 250 cm³, that's going to be 10 times more. So you're going to write moles of iodine, and it would be 1 into 10 to the minus 3 moles multiplied by 10. Remember, you found the moles in 25 cm³. So the original 250 cm³ sample, that's going to have 10 times more moles. So the answer comes out to be
0.01.
Okay. And then using those moles of iodine, double that, you'll find the moles of copper sulfate. So that was the last thing that you wanted. So it's going to come out to be 2 times 10 to the power minus 4 moles. I said, but make sure you're working as much as possible. Now the total, so we found the moles of copper sulfate, 2 into 10 to the power. 2 into 10 to the minus 2, right? Okay, is that clear?
Yes.
So next one is a total of 7.98 grams of copper sulfate is present in 10.68 grams of copper sulfate. Complete each row of the table to calculate the value of X. So amount of copper sulfate in this thing in moles. So divide by MR, it's going to be 7.98. TK divide that by copper sulfate, which is 63.5 is copper plus sulfur is 32 plus 16 times 4. And you'll find the moles. What do you get for this?
0.05.
Okay, this one is, are you sure it's 0.05 moles, right? That's the amount of water in this thing, in moles. So the rest of the amount is water. So how do you find the moles of water? The mass of water is going to be 10.68 minus 7.98 grams. That's, and divided by the amount of water, which is 18. Okay, so out of 10.68, 7.98 was copper sulfate. So the rest is water. So how many moles of water do we get?
0.15.
So we're getting 0. Now we need to find the moles of, so the ratio is that 0.05 moles of copper sulfate, they contain 0.15 moles of water. So it's basically 1:3, right? So that means one copper sulfate has 3 water molecules, so X is 3. And even for that, you're going to show your working. Don't directly just jump and write the answer. When you're attempting the paper, try to show as much working as possible. Okay, that's in whatever way, at least show some working. Okay, so X comes out to be 3. Is that clear?
Yes.
Yes, sir.
It's the next one, organic. Okay, suggest a name for the reaction that occurs when sucrose reacts with water to form glucose and fructose. So what is the name of a reaction where water gets added and the molecule breaks? Hydrolysis. So when water is used to decompose or break down a compound, that's hydrolysis. Remember, hydrolysis is different compared to hydration. Hydration is an addition reaction. In that case, water simply gets added. Nothing happens after that. But water gets added and it breaks down, that's hydrolysis. Now, if no catalyst is added to reaction Z, the reaction is very slow. Label the Boltzmann distribution to show the effect of adding a catalyst to the sample of sucrose and water molecules at constant. So this is the distribution of molecular energies. So there's a line that's called, so this line over here, that's your actuation energy. Now, particles that have energy that is greater than actuation energy, they're the ones that are going to have successful collisions. So at extremely high energies, the height is the number of particles. So most particles have low energy. Very few particles have very high energy. When you add a catalyst, what happens to this line?
Activation energy move to the left.
It decreases. So it becomes easier for the reaction to happen. So now even these particles would be able to take part in the reaction successfully, because if molecules don't have enough energy, they would collide, but they won't collide with enough force to break the old bonds and to form new bonds. So the particles, when they collide, they need some sort of energy to break the old bonds. That is why your wooden table is not burning, because the oxygen molecules are hitting it, but they're not hitting it with enough force. If they're able to hit with it at high temperatures, if the molecules are able to hit with it, hit the wooden chair or the wooden table with enough force, they would break the old bonds and new bonds would be formed and it will start burning. So every reaction has a minimum activation energy. Isko label kar lena. This is the catalyst one, catalyzed with catalyst. So explain your labeled diagram. Now I'm not sure what type of explanation there is. Show the effect of adding a catalyst. So I think this is what so we're going to write that the actuation energy decreases when we add a catalyst. So what the diagram shows is that now more molecules can take part in successful collisions, because previously only these ones were able to take part. So now more molecules have, or more particles have energy greater than actuation energy. Greater than actuation energy and can collide successfully or can have effective collisions. To your guess, let me just check how did they explain this. I think it was, where's the explanation? Greater number of sucrose molecules have energy greater. I mean, that's all you had to describe. And we pretty much did all of that. So the next one is explain what is meant by the term chiral center. What is a chiral center? Kya hoga? What's a chiral center?
Carbon to which 4 different groups or atom are attached.
Okay, so on which 4 different groups atoms are attached. So that is what 4 different group of atoms. And it will form an optical isomer. So on the diagram, label all the chiral centers with a star with an asterisk. So is this chiral? How many chirals do you have in this molecule?
3.
This one is chiral. I'm circling them. This one is chiral. If you're standing on this carbon atom, all 4 sides are different. Then you have this one is chiral. Then you have this one as chiral as well. So you've got 3 chiral carbon atoms. Determine the empirical formula of fructose. So that's 1, 2, 3, 4, 5, 6 carbon atoms. Hydrogens are 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So you've got 12 hydrogens and you need oxygens. That's 1, 2, 3, 4, and 5. Are we sure we have 5 or 6? 1, 2, 3, 4, 5, and 6. So that's basically glucose. The empirical formula is going to be C1H2 and O1. Explain what is meant by the term enthalpy change of combustion. So it's the energy that is released when what happens? When 1 mole, specifically 1 mole of a substance, burns in excess oxygen. Write the equation for the complete combustion of sucrose. So it's what's sucrose? What's the formula of sucrose? That's sucrose was this white crystalline solid C12H22O11 C12. So it was C12 and H22 and O11. So you're going to burn it and it's going to produce carbon dioxide and H2O. And there's going to be 12 carbon dioxides and there's going to be 11 H2Os, and you can balance the oxygens. That's 24 plus 11. That's what's 24 plus 11? That's 35. So you've got 11 over here. So you need 24. You could confirm, Carla, is this correct or not? 35 oxygens and 24 plus 11. I think that's 35. Hydrogens, that's 22. Carbons 12. Carbon 12. So it kind of looks fine. So moving to the next one, you're given the enthalpies of combustion of sucrose, glucose, and fructose. Use data in the table to calculate the enthalpy change for the reaction occurring when sucrose reacts with water. You should draw a labeled Hess cycle to show your working. So they're even asking for a fully labeled Hess cycle. So I'm just going to go back and so we need a labeled Hess cycle as well. The question is kind of really simple. Otherwise, it's simply what's happening is that you've been given the enthalpy. So let me write the equation over there. C12. I mean, what's C12? H22O11. So you've got C12, H22O11. There's one water molecule that's being added to it. And what's happening? The other thing that's happening is on the other side, it's you're getting this one. Fructose was this thing. Wait a second. Why is fructose over here different? So what's the difference between these two? They're kind of the same. So it is both of them are C6H12O6. So coming back to this, both glucose and fructose, they have the same molecular formula. I mean, you can count the atoms at the top. They have pretty much the same molecular formula. I said now there are two ways of doing this. One is the direct way. What happens if you're given the enthalpy of combustion of this thing? You're also given the enthalpy of combustion of this thing, and you're given the enthalpy of combustion of this other product as well. All these values are quoted. And can you tell me what is the enthalpy of combustion of water? Kirti, what's the value of enthalpy of combustion of water? You see your idea? What's the enthalpy of combustion of water?
Zero.
Zero. Remember this. That enthalpy of formation of elements is zero. Always. Make sure you remember this. And the enthalpy of combustion of things that have already combusted, that's zero. Like enthalpy of combustion of carbon dioxide or enthalpy of combustion of water is going to be zero, because water is going to react with oxygen to produce water again. I mean, nothing new would be formed. So that is zero. So you know the enthalpy of combustion of water as well. So what is the formula that when you know the enthalpies of combustion of everything, the products and the reactants, so it's basically the enthalpy change of that particular reaction is the enthalpy of combustion of the reactants, which in this case is C12H22O1 minus the enthalpy of combustion of the products, which you have fructose. I'll just write fructose and glucose. Okay, so you do reactant minus products. But over here, they're asking for they're specifically asking for you to draw the Hess cycle. So you're going to draw the Hess cycle. When I combust this, what do I get? I get carbon dioxide and water. So I'm going to get carbon dioxide and water. How many carbon dioxides? I'm going to get 12 carbon dioxides. So I'm going to get 12 carbon dioxides, and I'm going to get 11 water molecules. Plus there's one water molecule already there, so that's going to be 12 water molecules. And when I burn my products or combust them, I'm going to get the same thing. I'm going to get 12 carbon dioxides and 12 water molecules. That is what's going to happen. This value is minus 5643. While this one over here is minus 2805 plus it's minus 2810. So one path is equal to the other path. So that's my one path. That's the enthalpy change I'm looking for. And this is my other path. So these values need to change the sign. So it's going to be minus 5643. And the other ones would become plus 2805 and plus 2815. So in this specific question, they were specifically asking you to draw the Hess cycle. But the other way around, it's a simple formula, which is that if you know the enthalpy of combustion of everything in the reactants and the products, you can simply do reactant minus products, and that will give you the enthalpy change. But over here, they were specifically asking for the enthalpy change. So what do you get for this?
Minus 28.
Okay, so we are getting minus 28 kilojoules per mole. So next one is you've got hexane, C6H14 is a colorless liquid. 2 test tubes contain, so it's an alkane. And he says equal amounts of hexane. Bromine is added to both test tube. One test tube is kept in the dark and the other is exposed to sunlight. The table describes the appearance of each test tube. So since it's an alkane, obviously, it's going to react in sunlight. Mixture fades to pale yellow. So obviously bromine reacts. So test tube in the dark is kept cool and is not exposed to, explain the observation of the test tube kept in the dark. The observation is obviously, I mean, no change, right? I mean, they're looking for an explanation actually. So alkanes, I mean, it's a 2-mark question. I don't know what, explain the observation in the dark. Alkanes obviously don't react. I mean, we could give a lot of explanation for this. Don't react with Br2, or you can say it's unsaturated. that they don't have a double bond. And light is needed to form radicals, right? Why is free radical substitution possible? Because light is needed, UV light especially is needed to form Br radicals. So otherwise the reaction is not going to be, it's not going to be possible. So we had to explain the observations. The observations were already given. So make sure you interpret the question properly, that the observations are already given. So you don't have to write the observations. You have to explain why there's no color change. Because it's unsaturated, alkanes are actually saturated. Bromine only reacts with unsaturated double bonds. But it's the 2-mark question, kind of a vague question. We'll just have a check with this one, that no reaction, not enough energy. So that is somewhat we described over here, that light is needed to form the Br radical. So that kind of sums it up. You need light to form the Br radical. The other part is bromine radicals are not produced, or homolytic fission of bromine does not occur. So fine, that's that. I mean, no marks for the unsaturated part, that it's saturated. They weren't really looking for that. They were actually looking for this, that light is needed to form Br radicals. State the name of the mechanism of the reaction that occurs. So alkanes undergo free radical. They undergo free radical substitution. So what is free radical substitution? It's this one. It's let me just open this. So your free radical substitution happens it's this one, that because of light, because of UV light specifically, Cl radicals or Br radicals are produced, homolytic fission occurs, and these radicals don't have a bond. So they would like to bond with someone, they would need electrons. It's a chlorine atom basically. So the chlorine atom is going to attack the alkane, and it will steal the hydrogens from it. It will form HCl. The carbon would be short of a bond now, and carbon would like to complete its bonds. So it will steal chlorine atoms from a chlorine molecule and bond with it. Then Cl radicals are produced again. Those Cl radicals will do the same thing. They're going to attack the carbon again and steal hydrogens from it. So propagation will continue. At the end of the day, there's going to be termination, that any two radicals could simply join up. So everything is happening, free radical substitution. Give an equation which shows a propagation step in this reaction in which hexane produces this. So what did I tell you? That a Br radical is going to be produced, which is basically a Br atom. You've got a hexane molecule, right? So what will the Br do? Hexane is C6H14. So what will the Br radical do? The Br radical is going to attack this alkane and steal a hydrogen from it. It will form HBr. And as a result, this hexane would lose one of the hydrogens. So it will form C6H13, and it's going to be a radical. That is what's going to be.
C6H13 Br नहीं होगा?
नहीं, वो propagation step है ना. Propagation step में you have what you have in the propagation. In the propagation step, Br it comes next. Like once, let me write it over here. Now this radical is produced, right? So H13, it's short of one bond, right? So it will steal, like if there's a bromine molecule around, it will steal one of the bromines and bond with it. So it will become C6, H would become 13, and there's going to be Br. And another Br radical will be produced. This is also a propagation step. Acha, coming to your question, 1 second. What's your question? The first steps are slow. Once. Acha, the first steps, wait a second. The reason the first steps are slow is because it's the first step that needs energy, because it's hard to break the bonds. Now, once the bond is broken, the Cl is very electronegative, so it can steal electrons or steal hydrogen atoms from the other atoms all by itself. because Cl really likes to gain electrons. So what it will do is it will see the H electron being bonded with carbon. It's going to pull that electron and put it, it will try to gain that electron. So the first step is important because it's hard to break the first bond. So that's why most reactions, but it's not always. It's sometimes the first step is fast as well. Now moving to the next question, part C. Give an equation which shows the propagation step we did that, 1 bromohexane. It's this one. So we did another propagation step, and that's this one. 1 bromohexane has been produced. Give an equation which shows a termination step in the reaction that produces 1 bromohexane. So your reaction will produce a lot of radicals. So the radical could be C6H13, or it could be a Br radical as well. So at any point, the two radicals, because they're short of bonds, at any point they would simply get together and bond with each other. So that is a termination step. So that's how 1 bromohexane would be produced. Okay, is this clear? As the next one, you clear? Last one, is this clear? So next one is you've got A and B are different chain isomers with the formula C6H12. And remember chain isomers, chain alkene, sorry. A does not show cis stereoisomerism, and A reacts with potassium manganate 7 to form hexane 1,2 diol. So when are diols formed, we have to figure out what A is. So it's hexane is 6 carbon atoms, and it's 1,2 diol, which means 1 and another diol on this one. I'll just hold on one second. I say sorry, hello. I said so this one, it's forming a diol. So when do diols are formed? When you have oxidation of alkenes, mild oxidation. So the double bond must be at this point. A must be an alkene that has a double bond at this specific place over here. And so that is what the structure of A is. You can add in the hydrogens. TK, is that clear?
Yes.
So you can add in all the. State the conditions needed for this reaction of A. That's mild oxidation. Remember, mild oxidation gives you diols. I mean, the OH, in mild oxidation, OH groups get added like an addition reaction. So that happens in mild oxidation. So mild oxidation, that's cold, dilute, and acidified KMnO4. Now B reacts with hydrogen gas to produce hexane. Okay, that's fine. Name the type of reaction. B reacts with hydrogen gas in the presence of platinum catalyst to produce name the type of reaction. That's addition. That is what happens when you have an alkene. In terms of sigma and pi bond, describe any similarities and differences in the type of carbon-carbon bonds in B and the type of carbon-carbon bonds in hexane. So similarity and differences. So I'm not really sure what they mean by that. It's in terms of sigma and pi bond. So obviously B has 1 pi bond because B is an alkene, right? So similarities and differences in the type of carbon-carbon bond. So I'm not really sure. I mean, B has one pi bond, whereas hexane has all sigma bonds. So are they looking for hybridization or what? In terms of sigma and pi, I mean, you just have to describe in terms of sigma and pi bonds. So B just had one pi bond. That whenever you have a double bond, I mean, this is not B, but whenever you have a double bond, B was an isomer of this, so that also had a double bond. So whenever you have a double bond, there is one pi bond at least in that. So I'll check the marking scheme for this, like in terms of sigma and pi bond, how are they describing that? So I mean, that is exactly what they're looking for. That only sigma bonds in hexane, so that's fine. And B has sigma bonds and one pi bond. So I mean, you could have written it more clearly, but that is what they are looking for. So B had at least had a single pi bond. The rest were all sigma. I mean, we should have written that the rest are all sigma bonds. So what else? We've got this last question, which is CD and E are isomers of each other. I'm going to try and do this quickly. They're made by passing an alcohol vapor over an aluminum catalyst. So what happens when you pass an alcohol vapor over an aluminum catalyst? This is what happens. The alcohol turns into an alkene, Al2O3 plus heat. So draw the displayed formula alcohol used in the experiment. So the alcohol OH would probably be at what position? It's probably going to be at this position. I mean, it's 4 carbon atoms, right? All of them. So remember, the OH would be somewhere in the middle. Name the type of reaction. That's dehydration, or that's dehydration. The OH would be on this carbon atom because you're getting a double bond either on this side or you're getting it on this side. So of this carbon atom, all these double bonds are around this carbon atom, the second one. It's the second one. Okay, either it's on the left side or the right side. You can add in the H. You have to draw the displayed formula. Be careful. In displayed, you have to show every single bond. So you've got to show every single bond in the displayed formula, even the OH bond has to be shown. So that is what your displayed formula is. Name the isomers CD and E. So this is but2-ene. This one is also but2-ene. And this one over here is but1-ene. How do you differentiate the two but2-enes? What would you call this one and what would you call this one? Kya hoga? Like both of them are but2-enes, but how do you differentiate them? Great idea, any idea? इसका मैं जल्दी से बता दूं कि it's this one is cis. ठीक है, this one is cis and this one is trans. Because over here, the two carbons on the double bond are pointing in the same direction. Over here, the carbons are pointing in opposite direction. One is pointing downwards, the other one is pointing upwards. So cis and trans, so we've named them. And then you have this thing, last part. You've got this one. F is an organic molecule which has the formula C3H6O2. So this one is kind of a difficult question, C3H6O2. When F is heated with NaOH followed by H2SO4, the products G and H are made. So it's followed by H2SO4. So that is hydrolysis. It's breaking up. So this thing, there's an O2 as well. So this thing is breaking up. Samples of G and H are added to Na2CO3. So this is what's happening. Na2CO3, bubbles of gas. So G must be a carboxylic acid. So the first thing that indicates that it's a carboxylic acid. H has no reaction, so not a carboxylic acid. Sodium, it reacts, bubbles of gas produced in both cases. So H must be an alcohol. I mean, we know it's not a carboxylic acid. Who reacts with sodium? Sodium ke saath, it's alcohols. So with sodium, it's alcohols that react or it's carboxylic acids that react. So they react with this thing. But coming back to this, it's coming back to this sodium, this would be an alcohol. It's not a carboxylic acid because the first test was not positive, so it's not carboxylic acid. And this is a carboxylic acid because the first step said it's a carboxylic acid. And then alkaline aqueous iodine. So that means alkaline aqueous iodine gives a positive result with this structure. So it's giving a positive result with this one. So a final so complete to the table to identify the functional group, we did this. Remember, iodoform test is this one. Iodoform test, you get a positive result when you either have a methyl with a acetyl bond or a methyl with CHOH. So I chose this one because I already knew that it's an alcohol. So coming back to this one, we now have to name the yellow precipitate form, that's CHI3. Okay, when you do an iodoform test, the CH3 breaks off and it forms a yellow precipitate of CHI3. Achha, phir kya, draw the structures of G and H. So I know it's a carboxylic acid, it's a 3 carbon atom molecule. So if this thing, alcohol, has this structure, then there's only 1 carbon atom left. So there is going to be methanoic acid. But how did I know that this has 1 carbon atom? Because there were a total of 3 carbon atoms. 1 carbon atom went here and 2 carbon atoms went here, because 2 carbon atoms went over there because they had this structure. So the only way that's possible is that 2 carbon atoms are in this molecule and there's 1 carbon atom left for this molecule. So there's going to be a 1 carbon atom carboxylic acid, and this is going to be a 2 carbon atom alcohol. So you don't have any other carbon atom. So this R over here would most likely be just an H atom. So these are going to be your 2 possible structures of G and H, and that's about it. So G and H must be this one. So I'm just going to quickly recap this. That I knew it's hydrolysis. So I had a total of 3 carbon atoms. So either G will have 1 carbon atom and the other one will have 2 carbon atoms, or this one will have 2 carbon atoms, the other one will have 1 carbon atom. The first statement proved that G was a carboxylic acid because it was reacting with sodium carbonate. The second statement proved that this one was an alcohol because it was reacting with sodium. The third statement showed us that it must have this structure. It must have CH3 with CHOH. So that indicated that this must be the 2 carbon atom thing, and that must be the 1 carbon atom thing. So that must be the 1 carbon atom carboxylic acid. This must be the 2 carbon atom, this iodoform thing. So let's continue next time then. Okay, everyone.
Love you, sir.
Office.